Maybe some second here. I guess it should.
Do you want to use microphones?
Probably. It works.
Okay, it doesn't work.
Do you know if we should wait for recording to be started?
My friend.
Okay. Okay.
So we'll figure out.
Let's start. Let's get started.
Yeah. Okay.
Okay, I think let's get started with some introductory words. Can you hear me without the mic? Or it's better to use mic? With mic it's better. Okay. So let's start with some introductory words. Maybe the recording will appear, maybe not. It's not working. Okay, super. So we will present a tutorial about how to speed up your Python application or Python library with Cython and C++. So here's the slide with setup instructions so you can basically close the repo. The link is also in the shadow and follow the instruction from the README while we are doing some introduction. If you haven't done it already, and it's important to use conda or mini-conda to install the dependencies or mini-port because otherwise it may not be installed correctly. So a few words about us. We developed the extension for scikit-learn library with optimized implementations of classical machine learning algorithms. And we do this by implementing an efficient backend in C++ and then porting it into Python. And during this tutorial, we will try to show a little bit of our work, an example of how we achieve this. So we'll do this on the example of some simple machine learning algorithm linear regression. So during this tutorial, we will implement it from scratch and try to achieve better performance than in scikit-learn, but with some tricks. We will have a few practice sessions related to Cython and PyBind, so the theory will be mixed with practice so that it doesn't get really boring. So a few words about motivation. Everybody knows that Python is slow, but it appears to be convenient, and for many machine learning applications, people use it, basically for all. But the problem here is that when you train some machine learning model or deep learning model, you have to use a lot of computational resources. And while Python is an interpreted language, you can't do it efficiently. So you have a lot of overhead on executing every single instruction. Also, dynamic typing slows things down, and this global interpreter law, it limits the true parallelism so that you cannot, even if your program has multiple threads, actually only one thread can work on the CPU. So even if you have multiple cores, it's not really efficiently implemented in Python. And what is fast? Fast is the compiled languages, so C, C++, and we want to use the benefits of the languages, of these languages, compiled languages, and precompile some code and then use it in Python. So all this in Python. And this is actually how many libraries are implemented. And so basically NumPy, scikit-learn, and like PyTorch, I think so. They all have kernels implemented in Cython or C++ or in other frameworks, precompiled and then loaded in runtime. So as we will be working with linear regression, let's do some theoretical introduction. So with the simplest model, basically we have a matrix with feature vectors. Usually the number of objects is much more than number of features. Then we have target values that we want to predict, and we want to find the linear weights that helps us to predict the target value using the input features. So how we find it, we just minimize this objective, and let's derive a few formulas. So how we minimize this objective, you can write it in the following way. Then it's a convex optimization problem, so we can take the gradient and it should be equal to 0. Then we can open the brackets. Then after we simplify the equation, we get this new equation. And if you look carefully at it, you can see that it's actually just a system of linear equations. So on the left side, you have this x transpose x multiplied by beta, our coefficients, and on the right side, you have the x transpose multiplied by y. So it's basically a vector. And on the left side, it's a square matrix. And you need just to solve the system. So basically, one approach to solve linear regression, which is called normal variations method, is to find this matrix, find this vector, and solve this linear system. There are some problems with this approach because if there is some linear dependencies in the features, this matrix on the left side will not be full rank. So it cannot be used always. So in scikit-learn by default they use a different approach. So they have some iterative solver. But during this tutorial we will assume that this matrix will be full rank, everything will be good. And we will try to solve the problem in the following way. So we will have these three parts, and the time complexity of each of them will be different. And as we noted that the number of features is usually much less than the number of objects, the computation time, the time complexity for the first step will be np squared, which will be the most expensive part. Also, we need np for computing the vector, and the linear solver will work p cube. And during the session, we will basically focus on calculating the first two parts efficiently. So solvers can be really complicated. The first parts are not. So let's just focus on optimization of these two kernels. And for you to know that it's not just some arbitrary problem, it can be used for some classical machine learning application. So basically, this is how you can implement it simply in Python. And if you look carefully at these loops, you may notice that we can combine them to compute them together and get some performance benefit. But if you do this in the following way, I assure you that you will directly wait for your model to be fitted on some significant dataset size. So this needs to be optimized. And the first part is the first approach that we can use to optimize it is to use Cython. And Cython, as you may notice from its name, is a language that is really similar to Python, but the pipeline of execution is a little bit different. So we want to modify the code only slightly, but take the benefits of precompilation, static typing, avoiding some safety checks, and global interpreter log to speed up the performance. So if you look at the left part, there is example of some function in Python, and on the right part is the example of these same functions in Cython. So you may notice that there are only a few differences, and basically you can almost always use a Python code. Just copy paste the Python code in Cython and it will work. The question is how efficient it will be. But here we just introduce the static typing, and the pipeline of execution will be the following. So at first, your Cython code, which is similar to Python, will be translated to C or C++, depending on your settings, and C or C++ file will be generated. Then this code is compiled into a dynamic library, and this dynamic library is loaded at runtime, so you can call these functions using normal imports. So you may notice that the execution pipeline is much more difficult than with simple Python code. So you will need some tools to compile them and translate, and we will use setup tools for this. So with setup tools, you will have to run this setup.py file at the beginning of your execution, and you can mention these extensions here to compile, to translate and compile Cython and later C++ code. So usually when you have the wrapper and they have Python setup file, for example in NumPy, I guess, or somewhere else, you may notice that there will be some extensions that contains the Cython code that is compiled during this procedure. And also one way you can do it manually is to use Cython and C with a flag on your Cython file, and by this you can understand how your code is translated to C and C++, and this will be really useful in the tutorials. So let's start our practice session, the first practice session. I guess the setup instructions are in the repo. Has everybody found the repo? Right? Okay. Any problems with the installation of the setup, setting up the conda environment? Okay, let me just show how it looks. So basically, we will have here a few files. The utils.py file contains some auxiliary functions that we need for data generation, for benchmarking, and for computing baseline. So if you want to compute your matrix and matrix vector multiplication using just loops in Python, you can use this function, but basically we will compare with NumPy, which already uses some advanced libraries and kernels for computation. So we will use this function as our baseline, and basically when you call this in NumPy, it actually executes some precompiled code. And later we will look, so and here we just used our compare our implementation of this kernels and solver with the standard implementation of linear regression in scikit-learn to compare what speed up did we achieve. It's not apples to apples comparison, but we'll revisit. So during this session, so you have this solutions folder. You better don't look at it at the beginning because you will spoil the fun. During the first session, you actually need to modify this compute x6 xty naive function that takes as an input matrix with features, matrix with targets, the dimensions of the matrices, and the placeholders for the matrix A, which is x transpose x, and matrix B, which is x transpose y. and you just basically need to implement the function that fills these placeholders. Then, after you do it, you need to run the setup following the instructions in the README, and we'll see and run the benchmarks. So I suggest that you start with implementing this function, and remember that as a first iteration you can use just the Python code here and see how it will work. Any questions about what you should do? Any questions about the topic, like that I was discussed before? Yeah.
Can you make your recipe?
Sorry?
Can you make your recipe groups?
What tries?
Can you speak a bit louder?
Sorry. Actually, I'm jumping ahead, so I'll ask if that's wrong.
Oh, there's a microphone.
I was going to ask a question, but I think I'm jumping ahead, so I can ask
okay.
it at the relevant time.
Okay. So let me do the first part with you also. So we can just basically type the Python code here. So that's basically it for some naive implementation. It should be just like this at the beginning. So what should we do next? So by the way, why do we have this order of the loops? Just a head up question. Yeah.
Is it for cache reasons because you want to get a contiguous?
Yeah, exactly. Yeah, so we'll basically want to iterate through matrix X once, and as it's stored as a, we want to continuously read matrix X, and that's why we order the loops in the following way. So these reads will be continuous. Okay, so let's then try to compile it. So what we need to do is to go to our console and run this. Hope it will work. So here you may see that there is some lines with compilation happening, and now you need to export this practice session number, because we have the file with benchmarks that actually runs only part of the code, only part of the benchmarks that is implemented. So during the first test, we will just generate some data and compute the implemented benchmark functions that you implemented with the target time in Cython that can be achieved. So just run can just run tests at the beginning, just to check that it works fine, that we don't have mistakes in our implementation, and then run benchmarks. And you can see that NumPy takes 4 hundredths of a second. The Cython, for now, it's much slower, but the Cython target is 18 hundredths of a second. So we still can achieve. So you may say that it's a bad result, but if you uncomment this line and run it with a baseline, you will wait a lot of time. So I don't recommend you to do this, but I assure that the speed up compared to Python is already significant. So what do you, so who has tried to run execute it? For whom did it work? And just raise your hand, just to see. Let's follow. Okay, so are there any suggestions of what we can do with this code? Sorry?
Put some types.
Yes, we can do. So maybe we can just define I, J, and K, and everything else is typed here. So let's maybe try to recompile it. But I'm not sure that it would be much of a difference. But let's check. But I think the loops are already implemented pretty well. So it's a little bit of volatility here. So it's, yeah, I think it's at the same time. Oh, any other suggestions what we can do from the information from the previous sections? How to check that it was efficiently translated? Yeah.
Use the annotation.
You interacting with.
Use the annotation flag, so we're looking for interactions with the path and Java.
So I didn't quite get it, but what we can do is to just see how the code is translated. Is it your suggestion?
Yeah. So
Yeah.
compile with --annotate.
Yeah, of course. So let's just run this file. Thank you. And see what we get here. So just run the set Cython and C, and after we run it, it's there. Okay. After we run it.
It's not Cython, but it's very semantic.
Should be Cython as
I mean, if you try Cython, that's great to the HTML5.
Yes, that's exactly what we're trying to do.
Yeah, that's Cython, not satellite.
I see.
Okay, probably Cython. Probably, yeah, sorry for this. So basically when we do this, we get the HTML file, and here the yellows are the lines where we actually call the Python, where we fall back to Python. So it's a potential place for optimization. So if we look here, we can also do the plus to see how our code is translated to C or C++. So it's C++ in our case. And if we convert this line, we can see that here is a lot of commands, and basically you can see here is this raise buffer index error. So it's just the so here we just check that indexes are correct, and this is really heavy operation. So to get rid of it, we can disable bounce checks. And try to recompile it. And if we do this, it will be still some Python code. No. Just not here. So here now these lines are not yellow, meaning that we don't fall back to Python here. So now these lines are translated to fewer C code. So probably it's more efficient. So let's try to run it. Run the setup. So now it's already 2 times faster, just by disabling these checks. So, and we are 2 times slower than target. So let's look at the Cython code and understand what's happening here. So what is it? Just what is this line? What's happening here? Can you see it well by screen? Any suggestions? So basically, this thing is an index, and if the index is less than 0, we will add the size of the matrix to the index. So basically, that's actually a negative indexing in Python, and that's another if statement. So we don't. So if statements are slow when you try to compile them, because it's jump conditions and everything. So you want to avoid this, and to avoid this, you can add another disable another thing. It's wrap around. So it doesn't use negative indexing, and we can try to compile it one more time. Just translate it first, and now it's only this. So it's even fewer code. Let's set up and run the benchmarks once again. So the time didn't change, but still there are few commands. So if we look at this line, we can see that here we have a lot of things. And basically, this is happening because because we're working with a memory view here. So this is just a memory view on NumPy array. And because NumPy array can be stored when you do some slicing or other complex operation, it can be stored not continuously, but with some stride. And you want here you want to extract the element, you have to find the strides, then so basically read from memory to get the strides, then multiply them by so basically, yeah, read the strides and get the indexing in the array by using this complicated expression. So it's really time consuming. And also, what is the problem is that compiler cannot really optimize it because it doesn't, when the expression gets complex, it's hard to vectorize it and everything. So we want to avoid it. So we may assume that our matrix is continuous and use the raw memory instead. So here we have some pointers working with the, so we can actually work with raw pointers instead. So like we do in C. So now it starts to get more like a C. And here, let's just do the indexing in a different way. And see how, so we see how our code becomes less Python and more C, but let's see how it's reflected on the performance. So let's first also, let's make some const. Was it not modified one? No. Because I need to use pointers here, not the arrays itself. So you can check everything this by yourself. Let's check how it looks now. So now it's much simpler. And let's check the, let's run the setup and check the tests and performance. Awesome. Okay, so basically now we are really close to the target. So the main difference here is that we have much less memory dereferences because we don't look for the stride, and also this now the compiler might be able to optimize this. Because it's continuous reads. I'm not sure, like, I don't know, want to look at the assembly, but I think some optimization could be made here. And now, that's basically what we did in the in our implementation. So, any questions about the Cython, how you write kernels, what you can do there, how to optimize them? Okay, so you may know that it's you basically can achieve really good performance, but it might require some tuning from your side. So yeah, this is basically common pitfalls that we discussed. So let's start another part of our tutorial. It's about PyBind 11, and PyBind 11 is a little bit different from the Cython in a sense that it doesn't. So you don't use another language. You just have your functions implemented in C or C++. So you might have a separate library, and then you want to call them from Python, and you just do it using PyBind. So PyBind allows you to create wrappers over your over functions in your C++ library, so that you can call them from Python. So basically, here is an example from the PyBind website. So you just define some model and define the functions from the model with its declaration, and then you can just after you set up it, so it's compiled to the dynamic library, and in runtime when you run this import, the dynamic library is loaded, and then you just can call this function. So in the practice 2, we will write the kernel in C++ and call them from Python. So if you don't know C++, it's not really a big problem. So I hope it's the code will not be really complex, so you can manage it. And we will now look at the utils PyBind function, and basically utils PyBind file, and try to implement this function. So I guess the first thing that you need to do is to change the session number to 2, so that you run the correct benchmarks and tests. And then let's implement this function. Again, it should be really similar to what you did here with the pointers. Just with another. Basically, something like this. So I'll give you a few minutes. And yeah, after you do it, you just run the same setup and run the tests and benchmarks, and it should work the same way. So basically, it should somehow like this. Let's just set up the library. And tests. Oh.
What error are you getting?
That's the Pentax Dixit.
Jeez. So you get to the
It's the extension.
this should be
Hmm?
it's multiply.
Ah, that's very close, yeah. Sorry. Okay. Check it. And run the benchmarks. So basically, we're getting the same time as in Cython, but yeah, meaning that it's doing something similar. But here you have, I would say you have less unexpected side effects. So because it's just C++ code, it's compiled straightforward, and you expect more. You don't know, you don't have like GU and everything here, so you I would say it's a little bit easier to write it like this, because in Cython you might not expect something like bounce check wraparounds and maybe some G logs and everything. And I guess now, so any questions about just using raw PyBind? No? I guess then we can move to the next section of our tutorial about using the how. So now we're still far from NumPy, and let's try to understand how can we get closer to it and maybe even beat it, because now we are like 6 times slower than it. So I'll just
Sure. Can you bring
the charge.
no to my computer?
So you can have the mic.
Yes, how does it work?
And just turn it on in the bottom. So now it's on. Should be on now.
Oh, this is up.
Yeah.
Okay.
Can you show the slides?
Yes. Sure. Hello. Hello. Yeah, it's working. Yeah, so like we were seeing in the benchmark, the code that we generated was actually not any faster than NumPy. And so if we look at what NumPy and other libraries are doing under the hood, what they do is that they call a library called BLAS, and BLAS stands for Basic Linear Algebra Subroutines. So these are libraries that implement operations like, for example, matrix multiplications, matrix vector products, and so on. And the thing about these BLAS libraries, of which there are many different implementations, is that they are very, very fine-tuned to run fast, exploiting lots of characteristics about modern computers, like, for example, SIMD instructions, which are able to execute multiple sums or multiplications in the same time that a different computer would do one, or for example by trying to exploit how the data is loaded into caches in a way that there are fewer misses and lots of data reutilization. And NumPy, of course, is calling this library behind the scenes, and that's how it achieves this speed. These sort of operations are not part of the NumPy library. Now, linking a Python library to BLAS can be quite a complex topic, but there is a SciPy library offering this Cython BLAS interface to BLAS. Now, one caveat here is that BLAS was initially a Fortran library, not a C library, but we want to call these functions from C, and that means that we have to call them as if they were Fortran functions, and That means, amongst other things, for example, that we need to pass arguments by reference, meaning by pointers. There exists a C BLAS interface to BLAS. Unfortunately, it is not provided by SciPy, but if you want to experiment with using BLAS directly, there's another option if you want to check. So one particular caveat about Fortran in general is that the matrices in Fortran are usually assumed to be column major, whereas NumPy matrices by default are row major. And what this means, so when we take an array in NumPy, the array has potentially multiple dimensions, but behind the scenes this is just one contiguous array in the RAM memory. And it can be ordered, for example, by putting all the data from one row first, then all the data for the second row, and so on. And this is called row major, or it can be ordered another way, for example, by putting all the data from the first column, then all the data from the second column, and so on, and this is called column major. Now, if you think about it, the transpose of a matrix is the other matrix in the opposite order, so one tip if you want to play with these Fortran functions is to assume that your matrices will be transposed. And if you want to learn more about what kind of operations are offered by BLAS, you can check their webpage. So they have some pretty descriptive documentation about what they do, how much time complexity they take, and so on. And if you want to do the kind of operations that we were doing previously, recall again, we have a cross product and then a matrix vector product. And when we did this in NumPy, we were using a function for general matrix multiplication, in which we pass the same matrix, first transposed, then not transposed, but there exists such a function called SIRC, or symmetric rank K update, that can do this more efficiently than a general matrix multiplication. So it's a pretty simple operation. We will just drop a hint that it exists here and we will be calling it. And then there is another function that can do matrix vector products. And if you want to play with the tutorial that we are offering, then you are welcome to try to implement them if you are familiar with BLAS, but otherwise we are already providing a solution here that calls BLAS, and so we will take a look at what this file is doing. So as long as we are using Cython, we can get these functions easily from SciPy. Now there is an important distinction here that these are not Python functions, so we do not import them, but C import them. And once we have them, we need to call them not with Python objects, but with pointers to C data. So recall previously that we were using memory views, but these functions don't work with that sort of thing, they work with raw pointers, so you have to extract them, and then you need to play a bit with the function until you figure out the right order of the matrices and the right arguments and so on to get your calls working. So here is an example for Cython in which we are simply calling the functions with a function that is again cdef. This is not involving any Python whatsoever. This will translate into just a C call, and we will here now try to call this function in the main file that we were using. So we are already providing an easy way here to call the function. We will not go into much detail about how to write the function, but we will just copy it here. Yeah, and now notice that we are taking this function from SciPy through C import, and this tutorial also included some PyBind code. Now, in PyBind, this is not so easy to do, to take the blast function from SciPy, but it is possible. Or you can, if you want, try to link directly to blast by modifying the setup file if you would like to. But for PyBind or general Python C++ code, we can try to mimic what Cython is doing by importing a function, which is it provides a module, or let's say an attribute within a module called Pix C API, from which one can store function pointers, C function pointers, as in Python capsules. And that means that we can try to follow a strategy in which we need to declare the functions, we need to know the signatures, we simply define them as a pointer, and then at runtime we need to extract these pointers from the PyCapsules that are provided by Cython, and this way we can get the same blast functions working in PyBind 11 or in another arbitrary C++ or C Python extension. And just like for Cython, we are also providing a solution here that calls the necessary blast function with the right arguments. Also, just in case you might have noticed that these things, these functions have a trailing underscore, and one thing is that when you call a Fortran function from C, you usually do need to put the underscore in the name. Now, in this case, we are just defining the variables ourselves, but if you were trying to link to blast directly, you would need the trailing underscore, unlike in Cython. So to continue, we will just call this function that we provided in the earlier PyBind code. Oh, and if you are following the tutorial, this is practice number 3, so you need to set it like that.
Why picture here?
Test. Just test. Right.
Yes, sorry about that. So we had a technical problem here with the Cython code, but well, at least the pipeline code we got it to work, and yeah, from what you can see now, it is more an apples to apples comparison with NumPy. Both of them are calling the same BLAST library. They have similar runtimes. Now these runtimes have certain variants. Sometimes you might find that one is faster, sometimes the other is faster. But as you can see, we do have the advantage that we can use a more specialized function than what we use in NumPy. And now we are getting close to doing better. And now, if we go back to the idea of what the BLAST libraries are doing, is that, well, apart from exploiting the instruction sets of modern computers, they also play with the caches of the data. So the idea is that they try to load data into cache in an optimal manner, meaning that they do not need to load it more than necessary and reuse it as much as possible. And what we are doing here is two separate operations with the same matrix X. So the first one is a cross product, and the other one is a matrix vector product. And that means that we need to load the matrix into cache 2 times, which can be improved. So what could we possibly do here is called blocking, which is again the same that BLAST is doing, but we can also do it on ourselves, even with the same BLAST library. We can try to load the data into chunks, call one function, then the other with the block of data. And that way it will not need to be loaded more than once. This is something that again, we can do simply by calling the function separately, the way that we're doing with NumPy. And this is where tools like Cython or PyPy can help you a lot. And also, if you notice, again, we are calling this function on data, which usually has lots of rows and few columns. And we might see that BLAST can parallelize this, but it might not do it in the most efficient way. So the function might be optimized for different kinds of data sizes than what we are seeing here. So what can we do, for example, is that we can compute these matrices on multiple threads in parallel, and then we can sum them. Now this requires a different kind of parallelism that what BLAST is using, because that means that we need to allocate memory for each thread to hold this matrix. And as the data size grows in terms of columns, this is not a beneficial thing, but as long as we are restricting ourselves to inputs where there are lots of rows and few columns, we can usually do better with this parallelism. And one easy way to add parallelism here is to use the OpenMP library to parallelize things. Now we provide a setup file in which we are trying to add linkage to OpenMP, but this is not a very universal thing across different platforms. So hopefully you're using Conda for this, and if you're using Conda, then this should work out of the box for you, but otherwise trying to link to OpenMP, particularly in Mac, might require installing additional things, so we are dropping a link here from the documentation of scikit-learn that has instructions for developing their library in different platforms that includes linkage to OpenMP. But even if you do not have OpenMP, hopefully this will still work and provide a speed up for you. So the next practice is now to implement blogging into these kernels to speed things up. And again, we are providing a solution, and this time it might be a bit better to start with the pipeline 11. First things first is that we need to select a block size for our algorithm. So recall again that we want to load the data in chunks in order to reuse the caches, but that means that the chunk has to be small enough that it will fit into the cache and not get evicted. Yet it has to be large enough that it needs to provide good vectorization, and how to select a number here is an open question. So lots of what these BLAST libraries do internally is that they need to play and try to optimize all these block sizes for different kinds of computers. So we're unfortunately not going to do that here. We're just going to go with this magical number, which is 256 rows, and this should be a pretty good number for a laptop. It might not be good for a server, and this is highly dependent on your hardware. And we are going to iterate over the data in blocks of these many rows in parallel. In order to use parallelism with OpenMP, we can do this with this pragma parallel 4. It's quite easy to turn serial code into parallel with it. And what we will do this time is that we will call the same BLAST functions only on the block. And since we are doing it parallel, each thread will need to be computing the aggregates in its own memory. So they will not be writing to the same array in order to avoid conflict. And then at the end, we will sum the arrays to arrive at the final solution. Notice again that this is not the same way that BLAST is parallelizing things. It's a different way, more optimized for our purposes. And also, if you or depending on which BLAST library you are using, you might find that they also have their own threading backend for parallelism, and they might or might not play along with OpenMP. In which case, there exists a library, threadpoolctl, which can be used to disable parallelism of BLAST inside an OpenMP section, and we will be calling this function here just in case, but depending on your BLAST library, you might not need this. Now, the code here is quite long, so we will not be implementing it, we will just be including it, and now we will see the same thing in Cython. So we are also providing a similar function for Cython. Now, as far as Cython goes, we already saw that there are sometimes some performance bottlenecks that can be harmful for us. And what we are seeing here, which is a bit suboptimal, is that if we try to allocate memory with a C++ function in Cython, then the function can fail to allocate, and when it fails, it needs to throw a C++ exception, and this exception, usually you will want it to be translated into a Python error, and that means that you need to, again, acquire the global interpreter lock, which is a potential slowdown when you need to do this in a parallel section. Now there are some ways around it, but for example by switching into C style error checking, but for this tutorial we will not dive that deep, we will just use this Cython functionality except plus, which automatically can translate your C++ exceptions into Python runtime errors, which are recoverable. We will see that it does have some overhead, but it's not too bad. And now we will call this function from the previous files.
Cool. No site works. You can run tests just to check. Just run. Just to make sure. That's fine. Yeah.
Yeah, so for some reason now Cython worked. And yeah, as you can see, if we follow the same logic as Blast is doing, we can also try to adapt it for our purposes and do better than Blast. So as we can see here, if we try to reapply the blocking on our own end to our own particular problem, we can actually end up doing substantially better than even Blast with the simple separate calls to the relevant function. Yeah, as you can see, it's about twice as fast or 3 times as fast, or actually even more with pipeline. And the result is the same. Now, of course, this is up to numerical precision, and our approach is perhaps a bit less precise than others, but it's a very substantial speed up. So, yeah, the takeaway here is that you can get a lot of performance benefits for a library by employing compiled languages or trying to use automated tools to generate compiled code. For example, if you have a heavy workload that calls a function repeatedly, you can try to optimize it with a tool like Cython or Numba or Python, or if you really have lots of these and you need performance, you might want to write your things directly in C or C++ for less surprises and then call them with Cython or PyBind as wrappers. But whenever there is a library that is already optimized for your use case, it's better to use it. And usually you will find that lots of mathematical operations have been very thoroughly optimized the way that last libraries have. And you usually will not be able to outperform them with a simple loop in C. So use whatever libraries you find for your purpose. And just as a side note, we have this linear regression approach implemented in our open source library, scikit-learn IntelliX, if you want to give it a try. And yeah, pass it to Anatoly.
Yeah, one more important in this tutorial that what we did here is not possible if you use pure Python. So this idea with cache usages, if you use just calls from NumPy for matrix multiplication, it's not possible. So sometimes if you want to achieve a better performance, you have to go one level deep, even if there are some existing solutions. So and that's why it's important to be aware of these approaches. And yeah, if you have a small application, it's better that you reuse everything. But if you develop a library, I guess at some point you will come to a moment where you have to develop some C++ or Cython code for speedups. So yeah, I guess we have some time for your questions. Yeah.
Thank you for the workshop. Did you find more success using PyBind or Cython, or do you just use both as a mix?
So the problem is that if you have, personally, we also have a separate library that provides C++ interfaces, because when you work on some small devices, for example, you don't have enough capacity, enough resources to install Python and everything. You want it to be really low level. So we also provided one DAL library which has C++ interfaces. And once you have a separate C++ library, the only choice you have is PyBind. But if it's like a small kernel in some place and you want to support the whole C++ library, it's better to use Cython in this case. But if you have many things to optimize, I think it's better to use PyBind and C++.
Thank you.
Okay. So I hope after this tutorial you'll have more understanding on how actually these libraries work fast, and are not confused when you see some files in Cython, and you understand what's happening in setup and everything. So yeah, thank you for your attention, I guess. And feel free to contribute to these libraries if you want. They are all open source.
Thank you. I thought it was really brave doing live coding and stuff.
Sorry?
I thought it was really brave doing live coding and stuff.
Yeah,
But
it's
it
like
worked.
always. Yeah, we had a solutions folder. Yeah.
Yeah, cool.
Thank you.
I'm gonna grab some lunch.
Yeah?
Yeah.
Me too, I guess.
Yeah.
Me too.
it's pretty much.
But if it's not plugged in, it's really slow.
Yeah.